What's up guys, it's Misha. I bet you know parallel and series resonant circuits and might remember these fancy formulas or even how to derive them. Complete set? I wouldn't say so. There is one more formula that did not receive as much attention as its friends, but it must be known because it makes you see the resonant circuit differently. And today in ME class, we will talk about inductor and capacitor, voltages and currents at the resonance. Let's take, for example, a parallel RLC circuit and plot the output voltage as a function of the frequency. If we apply a current with zero frequency, essentially a DC current, and measure the voltage across the resistor, we will see 0 volts, because the inductor behaves as a short circuit element at DC. When we increase the frequency of the current source, we will see some voltage across the resistor. Increase more, and we will see higher voltage. And further increasing the frequency gives higher and higher output voltage until some point that is called the resonant frequency. And after that point, with further frequency increase, we will see that the voltage becomes smaller and smaller, approaching zero at very high frequency. And mathematically speaking, at infinite frequency, the voltage becomes zero because the capacitor behaves as a short circuit element. As a result of this frequency sweep, we see that the voltage has a bell-shaped profile with maximum at the resonant frequency. But what happens at this point? At the resonant frequency, the effect of the inductor and capacitor cancel out each other. And commonly, it is described as that a parallel LC tank can be seen as an open circuit. If it is an open circuit, then there is no current flowing there, and all the current of the current source flows through the resistor. Is it true? Well, partly. Let's redraw the circuit, emphasizing LC tank in it, and continue analysis. Okay, now we have a circuit with an emphasized LC tank. If we do KCL at the resonant frequency at this node, we will get that LC equals 0, because an equivalent impedance of a parallel LC circuit at the resonant frequency is infinite. That's why you can usually hear that a parallel LC circuit can be treated as an open circuit. But wait, what about individual inductor and capacitor currents? Are they zero? To answer this question, let's look at the impedance of the elements first. The impedance of the inductor is j omega L. If omega is a finite value and the resonant frequency is finite, then the inductor impedance is also finite, and when some voltage is applied to the inductor, we must see some current flowing. The same logic can be applied to the impedance of the capacitor. It is 1 over j omega c. If omega is finite, impedance is also finite, and if voltage is applied, some currents flow through the capacitor. Then the answer to our question is no, the currents are not zero. Then what is the value of the currents? Let's put aside the resonant concept and look at the circuit in general. What if I ask you to find the inductor and capacitor current? You would immediately tell me that the inductor current is V out over j omega L, and capacitor current is V out over 1 over j omega c. Or it can be rewritten like that. When omega L equals 1 over omega c, the sum of these two currents is 0, and this happens at the resonant frequency. So, if IL plus IC is 0, then current through the resistor is the current of the current source, and we can rewrite inductor and capacitor current in the following way. And at this step, you may recognize quality factor at the equations and eventually rewrite like this. Now, we can answer that the absolute value of the inductor and capacitor current is quality factor times input current. If you do similar procedure for a series resonance circuit, you will get that the voltage across inductor and capacitor are Q times higher than the input voltage. And now you have a complete set of formulas. And after this video, I think you will see the resonance circuit from a new perspective. At the end of the video, I'll give you a circuit to practice. Find the answers and leave them in the comment below. If you like this video, hit the like button, share it with your friends, and subscribe to my channel. It was Misha. Thanks for being in the class today. Bye.